Chapter 12, Electricity. Here is the index for this chapter. Section 12.1 covers electric current and circuit. Section 12.2 explains electric potential and potential difference. Section 12.3 is about the electric circuit. Section 12.4 details Ohm's law. Section 12.5 discusses the factors on which the resistance of a conductor depends. Section 12.6 is on the resistance of a system of resistors. Section 12.7 covers the heating effect of electric current. Finally, Section 12.8 explains electric power, electric current, and circuit. Here are some basic definitions. Electricity. It is a form of energy that can be easily changed into other forms. Electric current. This is the flow of electrons through a conductor. Conventional current. By convention, the direction of electric current is considered to be from the positive terminal to the negative terminal. It's important to note that the actual flow of electrons is from the negative terminal to the positive terminal. The SI unit of electric charge is the coulomb, represented by C. The SI unit for electric current is the ampere, represented by A. Continuing with electric current and circuit. Ampere. 1. Ampere is defined as the flow of 1 coulomb of charge per second. The formula is 1 ampere equals 1 coulomb divided by 1 second. An instrument called an ammeter is used to measure the electric current in a circuit. It must always be connected in series within the circuit. Electric current is expressed as the rate of flow of charge through a conductor. The formula is I equals Q divided by T. In this formula, I stands for current. Q stands for the quantity of charge, T stands for time. As a note, 1 coulomb of charge is equivalent to the charge of approximately 6 times 10 to the power of 18 electrons. Electric potential and potential difference. Electric potential. The electric potential at a point is defined as the amount of work done to bring a unit of positive charge from infinity to that specific point. The SI unit of electric potential is the volt, represented by V. This can also be expressed as a joule per coulomb. Continuing with electric potential and potential difference. Electric potential difference. In an electric circuit, the potential difference between 2 points is the work done to move a unit charge from one point to the other. The formula for potential difference is V equals W divided by Q, where V is the potential difference, W is the work done, and Q is the charge. The SI unit for potential difference is also the volt, represented by V. Electric circuit. An electric circuit is a continuous and closed path through which an electric current can flow. The slide shows a schematic diagram of a simple electric circuit which includes a cell, an electric bulb, an ammeter, and a plug key. There are different types of circuits. Closed circuit. A closed circuit is a complete, unbroken path that allows current to flow. The image shows a circuit with a battery and a lit light bulb, indicating a complete path. Open circuit. An open circuit is one where the path has been interrupted, breaking the flow of current. The image shows a circuit where the source of electrical energy has been removed, so the light bulb is off. This slide shows the symbols for some commonly used components in circuit diagrams. An electric cell is shown with a long line for the positive terminal and a shorter line for the negative terminal. A battery, which is a combination of cells, is shown as a series of long and short lines. An open switch or plug key is represented by a break in the line with 2 small circles at the ends, inside parentheses. A closed switch or plug key is shown with a dot inside the parentheses, indicating the path is complete. A wire joint is represented by a dot where 2 or more wires connect. Wires crossing without joining are shown with one wire looping over the other. Here are more symbols for circuit components. An electric bulb is shown either as a loop inside a circle or a more detailed bulb icon. A resistor of resistance R is shown as a zigzag line. Variable resistance, or a rheostat, is represented by a zigzag line with an arrow passing through it. An ammeter is a circle with the letter A inside. A voltmeter is a circle with the letter V inside. Ohm's law. Ohm's law describes the relationship between voltage, current, and resistance. It states that the steady current flowing through a material is directly proportional to the potential difference, or voltage, across it. This is expressed as voltage is directly proportional to current. This means voltage divided by current is a constant value, which is the resistance, R. This gives us the formula, V equals I times R. The slide also shows a graph of potential difference versus current for a nichrome wire. The graph is a straight line, which shows that as current increases, potential difference increases linearly, demonstrating Ohm's law. The SI unit of resistance is the ohm, which is represented by the Greek letter omega. 1 ohm is defined as the resistance of a conductor when a potential difference of 1 volt across it results in a current of 1 ampere flowing through it. The slide also has a cartoon that illustrates this concept. A character named volt is pushing another character named current through a narrow pipe. A third character, resistance, is squeezing the pipe, making it difficult for current to pass through, factors on which the resistance of a conductor depends. Temperature. The resistance of most materials increases as their temperature rises. This happens because the atoms vibrate more at higher temperatures, disrupting the flow of electrons. Length. A longer material will have a higher resistance because the electrons have a longer path to travel, increasing the chance of collisions. Cross-sectional area. A material with a larger cross-sectional area will have lower resistance. This is because there is more space for electrons to flow, reducing collisions. Mathematically, the relationship between resistance and these factors is as follows. Resistance, R, is directly proportional to its length, L. Resistance, R, is inversely proportional to the cross-sectional area, A. Combining these gives us the formula, R equals RCho times L divided by A. In this formula, RCho is a constant of proportionality known as the electrical resistivity of the material, resistance of a system of resistors. There are two primary ways to connect resistors together, in series and parallel. The slide shows diagrams for both types of connections. A series circuit connects components one after another in a single loop. A key feature of a series circuit is that a break anywhere in the circuit will stop the current flow entirely. Resistors in series. When resistors are connected in series, their total resistance increases because it is the sum of the individual resistances. The formula for the total or equivalent resistance, Req, is Req equals R1 plus R2 plus R3, and so on for all resistors in the series. For example, if a 2 ohm resistor and a 3 ohm resistor are connected in series, the total resistance is 2 plus 3, which equals 5 ohms. A parallel circuit is one that divides into 2 or more branches. The current splits and flows through each branch. An advantage of a parallel circuit is that if one component breaks, the other branches will continue to function. Resistors in parallel. When resistors are connected in parallel, the total resistance of the circuit decreases. This is because the circuit provides multiple paths for the current to flow. The formula for the equivalent resistance, Req, is 1 divided by Req equals the sum of the reciprocals of the individual resistances, which is 1 divided by R1 plus 1 divided by R2, and so on. For example, if two 6 ohm resistors are in parallel, the calculation is 1 divided by Req equals 1 divided by 6 plus 1 divided by 6. This equals 2 divided by 6, which simplifies to 1 divided by 3. Therefore, the equivalent resistance Req is 3 ohms. Heating effect of electric current. When an electric current flows through a wire, it causes the wire to heat up. This is a conversion of electrical energy into heat energy. The greater the resistance of the wire, the more heat is produced. This heating effect is utilized in many common electrical appliances, such as an iron, a kettle, and a hairdryer. The formula for the heating effect can be derived as follows. The power input, P, to a circuit is given by P equals V times I. The heat produced, H, is the energy supplied over time, which is power multiplied by time. So H equals V times I times T. By substituting Ohm's law, V equals IR, we get the formula H equals I squared times R times T. This is also known as Joule's law of heating. Practical applications of the heating effect of electric current. At the atomic level, as electric charges move through a wire, they transfer energy to the atoms, causing them to vibrate more rapidly. This increased vibration results in the wire heating up. The amount of heat generated is governed by Joule's first law, which states heat produced, Q, equals I squared, times R times T. In industry, this heating effect is used for applications like soldering, welding, cutting, and in electric furnaces. Electric power. Electric power is the rate at which electrical energy is consumed or dissipated in an electric circuit. The formulas for power, P, are P equals V times IP equals I squared times RP equals V squared divided by R. The SI unit of electric power is the watt, represented by W. 1 watt is defined as the power consumed by a device when 1 ampere of current flows through it at a potential difference of 1 volt. Thank you for learning with us.